All right, let's talk about resonance. So resonance is a pretty big topic in organic chemistry, so it's pretty hard to get all that detail in one video, so I'm not going to do that. Our goal for this video is simply going to be draw contributing structures and how to identify the most important contributing structure. So difficult part about resonance is you basically learn it through doing more and more examples and problems. And I recommend, if this is your first course in organic chemistry, pick up Organic Chemistry as a Second Language by David Klein. There's tons of resonance problems in there to practice the kind of skills that we'll be using today. I'm going to assume you at least know the basics of resonance, not go into the theory so much, and we'll try working some examples. So, first problem. Okay, so we're given a prompt like this. Basically, we're told that we have a certain formula, this formula here, and we're told that we have a basic skeletal structure, and we want to finish this structure and then basically draw the resonance structures. So the first thing you should always do if you're given a formula like this is you should first calculate your degrees of unsaturation. The degrees of unsaturation formula looks like this. So if you haven't seen this before, this basically is a way of calculating how many double bonds, triple bonds, or rings that you'll have in your molecule. Here, if we look at our formula, move it over here, and this is the calculation we're going to do. So the number of carbons we have, you'll notice, is 3, so 2 times 3 is going to be here. We have to add this 2. We have 1 nitrogen, and we have 4 hydrogens, but how do we deal with this negative charge? Well, the way that people have figured out is that basically you substitute another hydrogen in here and ignore the negative charge. So you treat this as C3H5NO. So that's why we have this -5 over here. Otherwise, you would get you get something like 2.5, where you get some sort of non-integer, and you can't have 0.5 double bonds or triple bonds. So you do this calculation and you find out that you have 2. So this tells us that we have 2 degrees of unsaturation. So we could have 2 double bonds or 1 triple bond or any combination of these. And you'll see that if you look at this skeletal structure, that it sort of already tells you here, because you know that there isn't the correct number of hydrogens around this. If this was a sp3 hybridized carbon here, you'd expect there to be 1, 2, 3 hydrogens around it. But there isn't, so you know that 1 double bond needs to go here, and 1 double bond needs to go somewhere around here. So your initial structure should look something like this. All right, so your question might be, okay, I understood there's a double bond here, and I understood there needed to be a double bond here, but what's going on here? Well, if you looked at that original structure, you notice that it needs to be negative. So the only, I guess, atom left that makes sense for it to be negative is going to be nitrogen. And you could do this same process through just drawing the Lewis structure, calculating the number of electrons you need, and filling it in that way. So this is really your starting point. This is your first resonance structure. And we want to determine the other resonance structures that this molecule has. So here there's essentially 2 ways that people commonly do it. The first strategy is what we'll call electron pushing. And this is the bread and butter of organic chemistry. This is the traditional method. The rules of electron pushing generally go as follows. And there's quite a few of them. So when you're talking about resonance, the moves you can make is first of all, when going between resonance structures, you need to conserve charge. So if this resonance structure here is negatively charged, any resonance structure we form afterwards must also be negatively charged. You need charge conservation. These are the 3 general arrow pushings that you'll do when you push electrons. This is what you'll look for. Now, how do you know when you screwed up? Well, first of all, if you break a sigma bond, it's no longer a resonance structure, because the sigma framework in a molecule needs to be the same between resonance structures. The other way to mess up is too many electrons to a second row element. So you remember the octet rule, elements generally want to have 8 electrons when they're second row, but if you put too many bonds to carbon, you get 5 bonds to carbon, say, that breaks the rules. You have 10 electrons on carbon. That's not possible because it doesn't have the orbitals to be able to do that. Remember, it only has a 2s and 3 2p orbitals. So that's a maximum of 8 electrons it could hold. And really, you want to keep track of your lone pairs and electrons. So we'll make sure to always include the lone pairs and the formal charges when you're starting out these problems. Okay, so what can we do with this? Well, we could do a few things. So you'll notice that if we're looking at the possible moves we can make, it says we could go from lone pair to pi bond. So really, you could move these lone pairs in 2 directions. We could go this way, or we could go this way, and that'll make a pi bond. The problem is that if you move these lone pairs down here, what you do is you create a pi bond here, and then you'll notice you have 5 bonds to carbon here and 5 bonds to carbon here. That breaks the rule, so we had to move this pi bond over here, and the only way it can move is on carbon. Similarly over here, the only way it can move is on oxygen. So the difficulty for a lot of people is that, look, like we just broke this rule over here, but we only broke it along the way to our final answer. So if we didn't do these second arrows, we would have broken the rule. But it's okay to break the rule in the first pushing, as long as you don't break the rule at the end. The result of the movement of these electrons will get you these 2 resonance structures. And everything should be in brackets, but I'm going to ignore that. And those resonance structures are going to be this and this. Actually, it's going to be this and this. So you'll see that the electrons here moved down, and then they moved up to this oxygen here. This has lost its negative charge, and now we have a negative charge on the oxygen. So charge was conserved. We went from a negative overall to a negative overall. Similarly over here, when this came down, we got this pi bond here. This became neutral. Again, I'm allowed to include or not include the lone pairs when I do these line wedge structures. And then electrons went up here, and this became negative. Okay, this is the traditional way to do the problem. I want to give you a second method just in case you ever get stuck when you're solving these problems. So the second strategy for resonance structures is what I'll call charge separation. And it comes from the idea that if you have a pi bond within a molecule, you could break that pi bond into 2 different charges. So you could break it into a positive charge and a negative formal charge. So generally the way you do this is the golden rule is you can break these pi bonds. I should specify here so you don't ever try to break a sigma bond. You could break pi bonds into their formal charges. And generally, you know that oxygen is more electronegative, carbon is less electronegative. So carbon will get the positive and oxygen will get the negative. And you know that if you have a positive and negative charge next to each other, those can be combined together to make a pi bond. Because again, that's how we just created this charge separation, is we broke up a pi bond. So if you look and you break up even further, you'll see that we can do something like this. So the question is, how did we decide to choose how to break up this over here? Well, the carbon-carbon pi bond, carbon, you can't make a choice like you did here, where you say, okay, carbon's positive, I'll make that positive. Oxygen's more electronegative, I'll make that negative. But your principle is that you could combine positive and negative charges to make pi bonds. So why would you break this into a negative and a positive here? You'd have 2 negatives next to each other. You can't do anything with that. So you basically make sure that they alternate. And here you have a framework to work with where you could combine basically the structure back together into the resonance structures that you actually want to see. Example here I'll show you are these 2. I should also have those double-headed arrows in the brackets, but I'm not going to put any brackets. Okay, so check this out. Here we saw we have negative, positive, negative. So we knew we could reconnect this to make a pi bond, or we could reconnect this to make a pi bond, and that's exactly what we did over here. Here we have alternating charges everywhere. We could either connect them here and here, and that'll get us back to here. Or we could say, all right, let's connect these, and that'll get us this structure. The advantage to using this method is that you can't make the same mistakes you made with electron pushing. That is, you can't accidentally create too many bonds to something, because there's no way to do that. You're just collecting charges. The downside is that you have more of these intermediates that are highly unstable, but you know those are just intermediates. You wouldn't consider either of these as the most important resonance structure. Okay, so hopefully you get good at electron pushing, but this is a good fallback strategy to use when you've basically gotten confused or you want to check out your answer. So the next question, the next part of this question was, which one of these resonance structures is the most important contributing structure? So here are our options. We have this, this, and this. Well, the first thing you'll notice is that each of them, well, actually I should tell you the actual rules first. So how do you rank resonance structures? Well, in particular, there's people that have figured out a bunch of great rules for this. In particular, I recommend looking at the book, The Art of Writing Reasonable Organic Reaction Mechanisms by Robert Grossman. If you want the rules in bulk, I recommend just looking at these, but these are a little bit complicated, so I recommend maybe you copy these down, and I simplified them to be essentially this. So this is the priority you'll use when you're ranking your resonance structures. The most important is that the octet rule is obeyed. So let's look at each of these three and see if the octet rule is obeyed. We already know that there shouldn't be too many electrons to each of these guys, so what we're really worried about is if there's too few electrons to any of these guys. But we see there's no positive formal charges, so that's not likely. So each of these three have a full octet. We don't have any electron deficient atoms, and we have charged species all around. So really, the next thing we're going to look at is rule number 4 over here. Which one of these atoms is bearing the negative charge? So here we have nitrogen, here we have oxygen, and here we have carbon. We want the most electronegative atom to be bearing the negative charge. That's going to be the most stable. If all things else are equal, so we know this will be the worst. And since oxygen is the most electronegative, we know that this middle structure will be the best. All right, let's try another problem. So here's the problem statement. Give it a try on your own first. You want to draw the 2 other contributing structures for the species. Okay, let's give it a shot. So again, I would redraw it, make sure you have all the hydrogens, have the lone pairs, the formal charges, just to make sure you don't violate the octet rule. So first way to do it is electron pushing. So you'll notice once again, you could either push left or you could push right. If you push right this way, you could create a pi bond here, but that creates too many bonds to this carbon, so you need to move this up here. Similarly, if you move left, you have the same kind of thing going on here. Or you could create a pi bond here, and then you have to move this pi bond up to this nitrogen. You should be seeing some patterns here. As far as your electron pushing goes, this kind of thing happens pretty often. The result of this movement of electrons will get you through these 2 species here. All right, as far as the charge separation strategy, let's look at what happens. So again, for your charge separation, you start at the same place with this resonance structure. Here we see 2 pi bonds that have one element being more electronegative than the other. So you could break those pi bonds into charges. Remember, when you break them into charges, you could combine positive and negative charges to make new pi bonds. So if we go along this way, we'll see that we could combine this, and then this, and we'll be stuck with a negative oxygen at the end. And if we go the other way, where we go this, then you'll see that we'll be stuck with a negative nitrogen over here, and these will be your two major resonance structures, other than the original one that we created. So again, the question is going to be, of these three resonance structures that we arrived at, which one is the best? So again, we look around, we see, is our octet rule obeyed? And we'll see that, again, there's no positive formal charges anywhere, and we obeyed all the rules in our electron pushing, so yes, all these have full octets. Again, no electron division atoms. We only have one charge, so again, we're forced to look at where our negative formal charges. Here it's on carbon, here it's on oxygen, and here it's on nitrogen. So once again, we get the same pattern as before. The least stable one will have the negative charge on carbon, and the most stable one will have the negative charge on oxygen. Okay, let's do another one. Give this one a shot. All right, take a few minutes to try that. Okay, so once again, you're given some sort of formula, so we should use this degrees of unsaturation principle to figure out how many double bonds, triple bonds, or rings we're going to have. This time it's not charged, so it's a bit easier. 2 times 3 plus 2 plus 1 for this nitrogen here, minus 5, so you know you're going to have 2 degrees of unsaturation. At this point, the other clues tell you that there is a C double bond N, so that's one of your degrees of unsaturation, and you know there's an NH bond, that's a clue, and really at this point you know from the NH bond that the nitrogen is only attached to one other molecule, so you have these carbons along in a chain, and you need another double bond because of this calculation over here. This 2 refers to 2 degrees of unsaturation, so 1, 2. We're good. The next thing we need to do is, once again, we need to go through and do the electron pushing. So if we do the electron pushing, we pretty much have this going on. So I'll call this method 1. Electron pushing. Shouldn't have that arrow really going on here. So again, this one's a little different since you're actually moving a pi bond here. And then since there's too many bonds to this carbon, you have to move this pi bond up to this nitrogen here. Again, when you're first starting doing this electron pushing kind of stuff, a lot of it seems unintuitive. You just got to get more and more practice. And then this will lead to this resonance structure over here. We have a positive carbon and a negative nitrogen. If you're using the charge separation method, which again I think makes more sense, then you have this bond with polarity, you have an electronegativity difference, you know that this will be split into a negative and a positive. Then you have a choice here with this carbon. You could split it into a positive and a negative, or a negative positive. Again, you want alternating charges because that's what you can work with. You can't do anything when you have 2 of the same charge right next to each other. So you can break it into this framework over here, and then recombine them back together to make exactly what you see if you did the electron pushing method. So both will make you arrive at the same final spot. So as far as stability goes, what's more stable? This or this? And I think it should be fairly obvious. This over here, this carbon does not have a complete octet, and this one is neutral. So this one has both full octets on everything and is neutral. This one is far superior resonance structure to this one. All right, there's usually some extra questions that get asked. They're not a lot of points, but I really want to make sure you guys know how to tackle them. So the 2 common questions are, what's the shortest bond in the molecule, and what's the strongest bond in the molecule? So let's take a small moment to talk briefly about bond length. In particular, there's a super common misconception in regards to bond length that we should address right now. So here is a table that tells you the bond lengths of things. I have sort of red boxed what I consider to be the most important bond lengths to look at in regards to what is a common misconception. So if you take these from this table and you arrange them like so, you'll see a pattern. Well, you'll sort of see a pattern. So take a look at this. You'll see that we've arranged them in increasing bond length, and you'll see that the shortest bond is not the triple bond. So the problem with this is that this is how a lot of students attack this kind of problem. A student will think, they'll remember back in general chemistry where someone told them that the shorter the bond is, the stronger the bond is. And then their gut instinct on that will be the triple bond must be the shortest bond in the molecule. After all, the triple bond is the strongest bond in the molecule. Now, what people were talking about when they told you that in gen chemistry was comparing single bonds to double bonds to triple bonds in general between the same species, all else being equal. So a carbon-carbon triple bond is indeed stronger than a carbon-carbon double bond, is indeed stronger than a carbon-carbon single bond. Here you can see that the bond energies are going up. The higher your bond energy, the stronger your bond. Here you could also see the relationship between the length. As your bond energies are increasing, as your bond order is increasing, your length is decreasing. And this is what they originally meant. The shorter bond is the stronger bond when you're talking about the same atoms and you're increasing the number of bonds to it. But if you look over here, you have energies all over the place. They're not very consistent with this trend over here. So you need to remember that when you're talking about this idea of short bonds or strong bonds, you're really talking about single versus double versus triple between the same things. Now, what are we talking about over here? So notice that the bonds to hydrogen between annular species are incredibly short. The reason for this is rather obvious. Hydrogen is very small, and the way it forms a sigma bond is it only has one orbital that could do that. It's going to be a 1s orbital. So it's going to be a very, very, very small orbital. So the idea here is that when you're talking about bond length, you're really talking about a few things. In general, anything bonded to hydrogen will be the shortest bond because, well, hydrogen is small and has a 1s orbital. Now, in general, when you're talking about other things, you'll see that it does meet the trend, it does meet your expectations, that triple bonds are generally shorter than double bonds, are generally shorter than single bonds. You just need to remember to update your worldview and remember that bonds to hydrogen will always be shorter. Typically, the more S character you have, the shorter your bond's going to be. And there you can see with the orbitals here that have that sp-sp interaction. Here we have that 1s interaction. And over here, as you increase, you're talking about sp3 and such like that. And remember, the p orbitals are a lot longer than s orbitals, so it makes sense that those bonds will be a lot longer. And as you're going across the periodic table, you'll see as you get more electronegative, those bonds are getting shorter because as you go across the rows, your atomic radii are getting shorter. So again, it won't be worth a lot of points, but this shows up every once in a while when we're talking about these resonance types of questions. All right, so with that little aside, let's do one more problem. Try this one out. So I'll give you a few seconds. Pause the video and work it out yourself. All right, let's get a little look. So once again, you want to use that degrees of unsaturation formula on this C3H3N, and you'll see that the calculation you do gets you degrees of unsaturation of 3, and you know that Cn is already going to be triple bond. So remember, a triple bond is 2 degrees of unsaturation. So you have one remaining degree of unsaturation to play with, and you already know that these carbons need to be attached to each other because nitrogen isn't going to be making any more bonds. So your starting resonance structure should look something like this. Then once again, we need to play our game of electron pushing or charge separation. Okay, so let's look at electron pushing first. So the first thing you can do is you can move the electrons up here, and that will get you this. And then once you've done that, you'll see that carbon's electron deficient, so you can push this pi bond over here, and then we'll be complete. Okay, again, the reason I don't like electron pushing so much is that this isn't obvious until you've done many, many problems. I think it's a lot more obvious when you're looking at charge separation. So if we're talking about our charge separation strategy, over here, and we have this carbon-nitrogen electronegative bond, we already know we don't have to intuitively feel that we need to push these electrons up here. We already know that we want to take our electronegative bonds and split them into positive and negative. And then once again, we're looking at that carbon-carbon bond over there, and we want to arrange it so that we have alternating charges. So we're going to break it up like this, and then we see from our sigma framework that we could form the pi bonds to make a new structure. And that's going to look like this. I'm going to get rid of this arrow because I know I just cut this off. It's also going to be the same thing as over here. So again, the reason I like the charge separation is that it kind of guides you along. We're here, there's no real intuitive way to know that you have to push these up here, and yeah, just take this pi bond, throw it here, and that'll move these electrons along. Again, you need to get good at electron pushing because that's what everyone's going to use, and that's what you're going to be using during your mechanisms, but always have this as a good backup. Okay, so again, now that we have, well, we should look at these two resonance structures, this one and the original molecule up here. You should know that this is better than this because this is electron deficient over here. This isn't a full octet, so this structure has the full octet, so it'll be the most stable contributing structure. And then from there, let's think about other potential questions that you could be asked. What's the shortest bond? What's the longest bond? And what's the strongest bond? Well, again, don't be persuaded to say that this is the shortest bond here, this triple bond over here, because you know that bonds to hydrogen are going to be a lot shorter because that 1s orbital is pretty small and hydrogen is pretty small. So you know that's going to be your shortest bond. You could use your bond order trend as you usually do from general chemistry and say that triple bonds are shorter than double bonds are shorter than sigma bonds when hydrogen isn't involved. And you'll know that this bond here will be your longest bond, and then your bond energy trend works for triple bonds having the most from general chemistry. So you could say this is the strongest bond. Remember that comes from here, we're going single, triple, double. Single, double, triple, you increase in the bond energy. So your triple bond will usually be your strongest, but it usually won't be your shortest because of these, well, CH bonds or NH bonds or what have you. All right, so hopefully this helps you out a bit. Hopefully you'll start considering this charge separation as a backup strategy, and hopefully you know from these rules over here how you're going to be ranking the importance of your resonance structures.